This is a graph of the total cases of COVID-19. You might have met this depressing line, but what if I told you we can predict how this curve will look like after this point? What if I told you that we can predict when the pandemic will end? This will change everything, from improving healthcare systems to opening global economies at the right time. Well, there is a way, the SIR model. This model is used to predict infectious diseases like COVID-19. Two scientists, Kermack and McKendrick, created this model in 1927 and published it in a paper called A Contribution to the Mathematical Theory of Epidemics. It involves three types of groups: susceptibles, infected, and removed. The susceptibles is the population who are not infected in the pandemic. The infected is the population who have caught the disease. The removed is the population who have recovered or have sadly died due to the disease. There is a set of ordinary differential equations that govern this model. ds by dt is the rate of change in the susceptibles, di by dt is the rate of change in the infected, and dr by dt is the rate of change in the removed. There are a few other components, namely beta, which is the transmission rate, and gamma, which is the recovery rate. When you divide the transmission rate by the recovery rate, you get a very crucial number called the basic reproduction number, or R0. This is the number of people that will catch a disease from an infected person. It is how scientists find the intensity of a pandemic like COVID-19 and predict its spread. If the R0 is less than 1, then we will see the infection dying out. If it is equal to 1, then the infection is stable. And if it is greater than 1, then the infection will spread. To understand this better, let's take a pond with lotuses. And let's say every day, one lotus produces 2 lotuses, which means that there is an R0 of 2. After 10 days, before you even know it, there will be more than 2,000 lotuses. A very similar case is with the latest reports of COVID-19, showing the R0 to be between 2 and 3. Now R0 and the growth will eventually decrease, and the curve obtained is called a sigmoid curve. The height of the point will tell us about the total number of cases, but the slope or a gradient of the point will tell us about the number of new cases per day. So when we plot the curve of the gradient or differentiate it, we get this curve, which is what governments are worried that this would flood our healthcare systems. But we can slow the growth and ultimately flatten this curve before it's too late by enforcing lockdowns and social distancing. I even tried it on my Python program with 2 different cases of social distancing, and the results seem to be pretty clear. This all showcases that the SIR model and R0 are significant breakthroughs in mathematics and epidemiology because they'll help us in fighting the COVID-19 pandemic.